Hello and welcome to Palisade Corporation's Webcast, Insurance Loss Modeling Using Simulation, presented by Dr. Domingo Castelo Joaquin, Associate Professor, Illinois State University. My name is Jameson Romeo Hall, and I will be your host today, and I will be available to help answer WebEx technical questions by chat. If you experience technical difficulties joining this WebEx session, please dial 1-866-229-3239. Alternately, you can email technical questions to support@webex.com. At this time, all attendees are in a listen-only mode. Please note that as an attendee, you are part of a larger audience today. The attendee list is suppressed to maintain attendee privacy. We will be holding a Q&A session at the conclusion of today's presentation. You may ask an online question anytime throughout the presentation today by clicking on the question mark icon located on the floating toolbar in the bottom right side of your screen. We invite you to sit back and relax and enjoy today's presentation. I would now like to introduce your presenter, Dr. Domingo Castelo Joaquin. One thing I have to do, and Dr. Joaquin, you now have the control.
Good morning. Can you see my desktop now?
Looks just fine.
Okay. Good morning. My name is Domingo Castelo Joaquin from Illinois State University. Thanks for tuning in today. My presentation is on loss modeling using spreadsheet-based simulation. In particular, what I'm interested in is giving a brief tutorial on simulating the present value of payments for losses covered by a one-year policy. Now, this particular problem is based on a problem posed by Stu Klugman in his classic text on loss modeling. Detailed documentation for the simulation model is appeared in published form last fall at the Risk Management and Insurance Review. You can obtain a copy of that from blackwellsynergy.com, or you may email me and I can send you a copy of the full article, which contains complete documentation. Now, what are the uncertain inputs in this model? Well, one is the inter-arrival times of loss events, the severity of losses, claim processing time, and the discount rate. So all of these are uncertain, and we want to combine all of those to come up with the present value of payments for losses covered by a one-year policy. So in this case, the timing of the payments are uncertain, so are the values of the payments. Now, inter-arrival times are assumed to follow the exponential distribution. So we will be simulating these inter-arrival times, and what we have is a one-year policy, and so when the time of the event exceeds 1 year, then those events are not covered by the policy. Here is our exponential distribution. The loss amount are assumed to follow the Pareto distribution. And this captures the idea that small losses are more likely than large losses. Claim processing time is assumed to follow the Weibull distribution. Now, in this particular case, we want to make claim processing time to be dependent on the amount of payment. In particular, we want to model in the idea that we would have longer processing time being more likely for larger claims. Okay, so it is where, okay, so the amount of the payment influences, okay, the distribution for the processing time. So if we combine the time of occurrence of a loss event and the processing time, what we end up with would be the timing of the payments. So in this particular case, for example, the event which happened second actually gets paid first. Okay, so that is how we generate these random payment amounts as well as random time of payments. Now, what we want to do is to take the present value of this. Okay, so and to do that, what we do is splice the timeline into various components, and these are interpayment times. Okay, so what we will be doing is we will be defining short rates for each interpayment period. Okay, so this is what governs the short rates. And once we have all the short rates for all interpayment periods, then we can calculate the present value factors. Here's our distribution for the short rates. And this is what our spreadsheet would look like. So we have in here our inter-arrival time for loss events. And here would be the timing of the event, the loss amount, time between occurrence and payment. Okay, so in the end, our objective is to take the present value of these payments and find the characteristic of the present value of aggregate loss payments. So we start by simulating inter-arrival time of loss events. We take the cumulative sum of these inter-arrival times to come up with the dates for the loss events. Loss amounts are obtained, okay, so using Pareto distribution. Okay. Time between occurrence, okay, so and payment. This is coming from the Weibull distribution. Now, if the loss event date exceeds 1 year, then those particular events are not covered events. And so the indicator variable over here is equal to 0. These are the covered events. Okay, so now for covered events, we want to obtain, okay, so the timing of the payments. The timing of the payment is obtained by summing two items, the time of the loss event and the time between occurrence and payment. So the sum goes here. Okay. Now, what we do next is to sort out this timing in here. Okay, so that is important when we generate the present value factors shortly. Okay, so these are sorted out from earliest to the latest, and the reason is that we want to be splicing the timeline shortly. Now, we do this using a command in Excel called small, and which is actually a very nice command, and that saves us having to write a macro just to do the sorting in between simulations. Okay. Now, so after the sorting, what we want to do is you splice the time up. Okay, so this would be the interpayment times, and then we generate the short rates for each of these sub-intervals. Now, once we have generated those short rates, we can produce these present value factors. Okay, so we combine all the short rates applicable to these splices in time to come up with these present value factors. Okay, now what we want to do is, well, suppose we want to calculate the present value of specific payments. So, for example, this first loss event, okay, so the loss amount was $203.96. Okay, so what we want to do next is, well, we find out, well, when is this particular claim ultimately paid? Well, that would be in 1.5 years. Okay. The next thing we do is we want to associate with this the appropriate discount factor. So you go to the next column and find out when does this occur. Well, it's over here, 1.56. And corresponding to this timing is this particular present value factor. So what we want to do is you want to multiply this 203.96 by 0.8913. Okay, so we do that using VLOOKUP. Okay, so VLOOKUP function to identify this amount, and the product is then what we register in that last column. Okay, so that is done for all of this. Okay, so items, and we aggregate the present value of each of the payments, and we come up with the present value of aggregate lost payments. Okay, so then we set our simulation settings. We used 10,000 iterations in the sample, and after we run the simulation, okay, so our first display is the summary output. Now, when you get the summary output, it is good to first check at the last column and see whether there are any errors. And in this particular case, okay, so you get an error message, and it says error is 67. Okay, so now when there is an error registered, that means that a calculation wasn't carried out. Okay, so in this case, 67 times. Okay, so now what does this mean? Well, out of 10,000 iterations, 67 times they did not calculate the short rate. And so there is not necessarily anything wrong with that. Okay, so there could be something wrong or maybe not. In this particular case, there is really nothing wrong. And the reason is that during the iteration, it turns out that in 67, okay, so of the 10,000 iterations, the losses occurred after the policy expired, and so we didn't have to calculate the short rates. So that is what explains this. So if there's an error message, this is an error message which is supposed to be unexpected. Okay, so it is expected error, and this one is fine. Okay. Now, suppose we have gone beyond those error counts, so we have no unexplained error counts. Then you go to the other numbers in your outputs, and you want to check whether the numbers seem too small or too large or have the wrong sign. Okay, so these are errors which at-risk will not be able to detect. Okay, so but you should be able to figure out. Okay, so since this would now fall under your expertise. Okay, so so for example, you want loss figures to be non-negative. Okay, so if in the summary output you see, okay, so negative losses, then okay, so you might want to check your model. Now, you would want to see whether the numbers make sense relative to the other numbers. So, for example, retained loss should not exceed aggregate loss. Next, you want to look whether a statistic looks right by itself or in relation to other statistics. So, for example, if the inter-arrival times are exponentially distributed, then the average number of losses per year should be close to the variance of the number of losses. Okay, so in other words, the number of losses, okay, so should be approximately Poisson distributed. Okay, so if that is not happening, then you want to check, okay, so the underlying cell formulas. Okay, so suppose everything looks fine, then you can proceed to examining the variable of interest. Okay, so the output cell of interest in our case would be the output cell containing the present value of aggregate loss payments. Now, we might be interested in what is the average present value of aggregate loss payments. We could also be interested in what is the probability that the present value will exceed a specific value, for example, the target premium for the policy. We may also want to answer the question, well, how do we make the distribution more desirable? Well, in this case, the tornado diagram would be useful. Okay, so the tornado diagram gives us the ranking of input variables in terms of influence on the output variable. Now, in our case, the most influential variable happens to be loss severity. Okay, so this is our Pareto distribution. Okay. Now, followed by loss frequency. Now, this tells us that in terms of administration, okay, so what the relevant department in the agency could be the loss control department in order for us to influence, okay, so our loss severity and okay, so our loss frequency. Okay. Now, another important factor is claim processing time. And in this case, the claims processing department, okay, so may have ideas about, okay, so how to manage this. Okay, so now, of course, we don't want to delay processing, okay, so in order to simply reduce the present value of aggregate loss payments. But this also tells us that when you have a partial model, now one can come up with some strange policy recommendation. Okay, so in order to properly assess this, we need a larger model, which not only models loss payments, but also revenues. Okay, so now let's go to the next item, discount rates. Now, the appearance of discount rates at the bottom was somewhat surprising when I ran this simulation. At least it was surprising at first, because when we're taking present values, it would appear that they should be very important. Well, in this particular case, it turns out not to be that important just for this problem, and basically the reason is that most payments are made in a short time. So now this means that there isn't much opportunity for the power of compounding to assert itself. Now, excuse me, and now another thing is that the one-year policy period usually would have elapsed after 6 loss events. Okay, so now if we had other problems, okay, so other settings, then discount rates would be would be more important. Okay, so those are the factors that are important in determining the present value of aggregate loss payments. Okay, so this, okay, so again, is based on Klugman's okay, so loss models from data to decisions. Okay, detailed, okay, so detailed documentation is given in my article published at the Risk Management and Insurance Review. Okay, so you may download it from Blackwell, or you can email me if you wish to have a copy. Okay, so I'm now ready for questions.
Oh, that was great. I do have a few questions here.
Okay.
I think what we'll do, I'll just leave your screen up.
Okay.
And then I'll read these questions.
Yes.
What distribution would you use for medical malpractice losses for a hospital? How would I figure total losses at a 75% confidence level?
I I am not okay. So I am not an expert on medical malpractice insurance, and so my suggestion would be to consult an expert on okay, so on those okay, so on those matters. The yeah, our simulation modeling, they are only as good as the assumptions that get into it, and the specifics of the problems will determine how we will or which distributions we would be using.
Okay, thank you. I have another question here. Why do distributions sometimes give negative values when I have truncated the min of the distribution to 0?
I will need to see how that your function is is defined. Now you may do some truncation in the parameters, but if the distribution itself admits negative values, then the final distribution that you get may admit negative values. But if you wish, you can share your model with me after the session, and we can look at it.
Oh, good, because I know who asked that. I'll send that link to you. And should we give it another minute for more questions?
Okay.
Let's see. We'll just give it one more minute.
Yes.
Well, I don't see any more questions coming in. I know that wasn't a minute, but...
Okay. That's fine.
I think that might have been our... yeah. Well, that was great.
Yes.
We really liked this. And thank you very much for coming. And thank you for this fine... here's another question. Good. See? Good. Can the slides be made available?
Yes. Yeah. I'll post. Okay. So I'll post the slides. Okay. So
Sure,
yeah, you can contact Jameson.
Sure, yeah, just contact me and I'll send them along. That would be great. Well, very good. Thank you, Dr. Joaquin.
Well, you're welcome, and thanks everyone for attending. Okay, so well, I'll just well, if you need, if you want a copy of the article, you can email me or you can go to Blackwall. Okay, so you can, okay, so also email for, okay, so if you have other questions, okay, so slides, that's fine. Okay.
Very good.
Okay.
Okay.
Well, thank
you.
you. Yes, you're welcome.
Thank you. Bye.
Okay. Bye.